Welcome to the class. We have seen till time about Brayton cycle, and also we have seen about the ideal Brayton cycle, which is air standard cycle. These cycles are also called as shaft power cycles, since the network whatever we calculate is available at the shaft. Now after considering the ideal cycle, we will move on towards the Brayton cycle with non-ideal components. Specifically, we mean here as the non-ideal compressor and non-ideal turbine. So the real compressor and real turbines will be considered. So accordingly, the processes associated with the compressor and turbine will get changed. So let us consider first the thermodynamic cycle for the non-ideal components. Here, as we know, we have this as ideal cycle, where we have first compression, isobaric heat addition, isentropic expansion and isobaric heat rejection. So this was minimum temperature and pressure, this was maximum temperature and pressure. Now we are going to consider the non-ideal compressor. So if there would have been ideal compressor, then this would have been the point at the end of the compressor. So let us consider it as 2 dash, which corresponds to the ideal point at the end of isentropic compression. But in reality the process is not isentropic, so the process will follow such that entropy will increase, and we will basically come along the same pressure, which is basically P2 dash is equal to P2 is equal to P3. So the pressures are same. So however, we will come to higher temperature and higher entropy point, which is 2. Similarly, in case of expansion, we will start with 3, but we will not end with 4 dash. So but we will end at higher entropy point, since the process 3 to 4 dash is isentropic and we are considering real process. So 4 is the real point at the end of isentropic compression. So this is the thermodynamic cycle corresponding to the non-ideal components. So let us consider the processes here. So as we have told, process 1 to 2 dash is isentropic compression process, but the process 1 to 2 is actual or real compression process. Then we have 2 to 3 is isobaric heat addition. This process is still ideal for us. Since we are considering static properties, we are going to discuss about it in the next chapters. Then the process 3 to 4 dash is isentropic expansion, and 3 to 4 is actual expansion. Then we have 4 to 1 is again isobaric heat rejection, and this also is an ideal process for us. So this is how we have the thermodynamic cycle for the processes of compression and expansion if they are non-ideal. Now let us move to the next point, which is component efficiencies. Since we have considered non-ideal components, which are compressor and turbine, we have to define their efficiency. So let us plot for the reference TS diagram as what we plotted. So T is on y axis, entropy is on x axis. So first we will plot the real process 1, 2 dash, 3, 4 dash, and then this is 2 and this is 4. So compressor efficiency is denoted by NC eta C, which is again also called as isentropic efficiency of compressor, and it is ideal work input to the actual work input. Actually, in case of compression, we are supplying the work to the system. So if efficiency is not the ideal, which is 100%, then we mean that actually we need to supply more work than the ideal work. So the efficiency for compressor has ideal work in the numerator and actual work which is higher than ideal in the denominator. So compressor efficiency becomes H2 dash minus H1 divided by H2 minus H1. So it is Cp into T2 dash minus T1 divided by Cp into T2 minus T1. So isentropic efficiency of compressor is T2 dash minus T1 upon T2 minus T1. Having said this, we will move towards the next component, which is turbine, and again we are considering it to be a real turbine, and its efficiency is eta T, isentropic efficiency of turbine, and turbine is a work producing machine. So ideally it will produce more work than the actual case. So actually it is going to produce lower work. So we have actual work output in the numerator and ideal work output in the denominator. So isentropic efficiency of turbine is basically H3 minus H4 divided by H3 minus H4 dash. So it is equal to Cp into T3 minus T4 divided by Cp into T3 minus T4 dash. So eta T is equal to T3 minus T4 divided by T3 minus T4 dash. So these are the two formulas which we should be using for rest of the part of this non-ideal component chapter. This in principle, while solving the example, or in reality we would be knowing the compressor efficiencies or turbine efficiencies, and using that we have to estimate the performance of the cycle or the engine. So let us start with state estimations. We know we did it earlier also in case of ideal. So now we have to repeat it in case of real cycle. Here as well we say that few things will be known to us and we have to estimate rest all the things from the known things, and this is what we mean that estimation of state variables. So 1 to 2 dash to 2 to 3 to 4 dash to 4 to 1. So the known things as what we had considered was Rp, T1, P1, T3. So practically beta is known to us, gamma, Cp. These were the known things in case of ideal. Along with that, now let us feel that we know eta T and eta C. So knowing these things, we have to find out the rest of the quantities at all the corners of the cycle. So let us feel that we have to know things at state 1, and at state 1 P1 and T1 are known. So we don't have to calculate anything. So at state 2, since we are considering real case, so we are not considering 2 dash, so it's a point 2. So we have to find out properties at 2, but we know P2 is equal to P2 dash, but still we know P2 dash is equal to Rp into P1. So knowing this, we know P2, basically P2 dash and P2 are same. Now we have to find out T2 is the temperature at state 2. So for that we have to first estimate T2 dash, and we know that T2 dash upon T1 is Rp raised to gamma minus 1 upon gamma. So this leads, for ideal case, T1 into Rp raised to gamma minus 1 upon gamma, and we have seen that compressor efficiency is basically ideal work input divided by actual work input, and then the formula was T2 dash minus T1 divided by T2 minus T1. Knowing this formula, we can write T2 is equal to T1 plus 1 upon compressor efficiency into T2 dash minus T1. So knowing this, we can calculate T2 as T1 plus 1 upon compressor efficiency into Rp raised to gamma minus 1 upon gamma minus T1 into T1 minus T1. So it practically becomes T1 can be taken common from everywhere, and it becomes 1 plus compressor efficiency into Rp raised to gamma minus 1 upon gamma minus 1. So this is how we can estimate temperature at the end of the compression and also pressure at the end of the compression. So now we have to estimate variables at state 3. There would be again two possibilities that we would be knowing T3, and anyway P3 is equal to P2 dash, which is equal to Rp into P1. So in this case we don't have to estimate, but if instead of that we are given with Q in, then we know that Q in here T3, or we will write, we would know T3 or Q in. So if Q in is known to us, then kilojoule per kg of Q in is equal to Cp into T3 minus T2. So we can know T3 here as T2 plus Q in upon Cp. So this is how we would have known the temperature at the exit of the combustor. Now let us derive the expression for properties at state 4. Again, if it is P4, then it is known that it is equal to P1, but in case of T4 it is not known. First we have to find out T4 dash, and we know T4 dash upon T3 is equal to P4 dash upon P3, which is 1 upon Rp bracket raised to gamma minus 1 upon gamma, and this leads to the fact that T4 dash is equal to T3 upon Rp raised to gamma minus 1 upon gamma. So we know now T4 dash, but we have to find out T4. So we will use the turbine efficiency formula, which says that turbine efficiency is equal to H3 minus H4 divided by H3 minus H4 dash, which is practically T3 minus T4 divided by T3 minus T4 dash. So T4 dash is equal to, so T4 is to be estimated, so T4 is equal to T3 minus eta T into T3 minus T4 dash. We can take common T3 from everywhere. Before that, we can mention it as T3 minus eta T into T3 minus T3 upon Rp raised to gamma minus 1 upon gamma. So it is T3 will be taken as common, so 1 minus eta T into 1 minus 1 upon Rp raised to gamma minus 1 upon gamma. So this is how we will know the pressure at station 4 and temperature at station 4. So from the known variables or known values of the quantities, we can find out the unknown values of different quantities. Knowing this, we can then find out what is the work and heat interaction in the process or in different processes of Brayton cycle, knowing the different state variables as what we had just now found out. So this is the cycle which is known to us, and from this cycle we can calculate WC, which is the compressor work, and for us compressor work at this moment is equal to H2 minus H1, or in other words, we know that ideal compressor work is WC dash, and that is H2 dash minus H1. Either knowing the formulas, we can calculate it as H2 minus H1, and which is rather WC is equal to known to us as Cp into T2 minus T1, but we know T2, which we have derived formula for T2 as compressor work is equal to Cp into T2 is T1 into 1 plus 1 upon compressor efficiency into Rp raised to gamma minus 1 upon gamma. So this is just T2, and then we have minus T1. So we can take T1 common from everywhere. So it will be CpT1 into 1 minus 1 plus 1 upon compressor efficiency into Rp raised to gamma minus 1 upon gamma minus 1 minus 1. So this one and this one would get cancelled. So we have compressor work is equal to CpT1 upon compressor efficiency into Rp raised to gamma minus 1 upon gamma minus 1. This is how now we can find out the compressor work. We would have also found out compressor work in the same case by considering compressor efficiency is equal to Wc dash upon Wc. So Wc is real compressor work, which becomes Wc dash divided by compressor efficiency. So real compressor work is 1 upon compressor efficiency into Wc dash, and Wc dash is H2 minus H1. So Wc is equal to 1 upon compressor efficiency. We will take Cp into T1 as common. So CpT1 into T2 dash upon T1 minus 1. So real compressor work is 1 upon compressor efficiency into CpT1 T2 dash minus T1 divided by T1 is Rp raised to gamma minus 1 upon gamma minus 1. So this is how we can find out compressor work in two different ways. As said earlier, if Q in is not known to us, we can find out Q in as Cp into T3 minus T2, but we know T2 is equal to T3 is as it is. So we know T2 is equal to T1 into 1 plus 1 upon compressor efficiency into bracket Rp raised to gamma minus 1 upon gamma minus 1, and all the brackets complete. So this is how we can calculate the Q in from known T3 and known T1. Further, we can also do one thing. We can take T1 common and say Cp_T1 is equal to T3 by T1 minus 1 plus 1 upon compressor efficiency into Rp raised to gamma minus 1 upon gamma minus 1, where T3 by T1 is said by us earlier as beta, which is basically T max upon T min. So let us see that, and then this becomes Q in formula for the case where we are having non-ideal compressor. Now we will work out in case of turbine, and then we have to find out real turbine work, and real turbine work is H3 minus H4. So again we can write down it as Cp into T3 minus T4. So it is equal to Cp into T3 and T4. For us, we know the formula for T4, which was actually T3 into 1 minus eta T into 1 minus 1 upon Rp raised to gamma minus 1 upon gamma, and all the brackets are then complete. So we can take Cp T3 as common, and then we can say that Cp T3 into 1 minus 1 plus eta T into 1 minus 1 upon Rp raised to gamma minus 1 upon gamma, and then all the brackets complete. So this is how we can find out. Further, here as well we can adopt the other method where we know turbine efficiency is actual turbine work divided by ideal turbine work. So actual turbine work is turbine efficiency into ideal turbine work, which is Wt dash, but here this 1 and 1 will cancel. So we have Wt is equal to Cp T3 into eta T into 1 minus 1 upon Rp raised to gamma minus 1 upon gamma. So further, if we find out by alternative method, then we have Wt is equal to eta T into H3 minus H4 dash. So we get eta T, we can take T3 common from here and Cp also common. So it will become 1 minus T4 dash divided by T3. So we get same formula for turbine work as what we have derived earlier. So it is Cp T3 eta t into 1 minus 1 upon Rp raised to gamma minus 1 upon gamma. So we get the turbine work by two ways, as what we got compressor work in two ways. Further, we can also evaluate the compressor, the heat output, and which is Q out, and Q out is H4 minus H1, which is Cp into T4 minus T1, and then we can also write T4 what we have derived, and T4 was equal to T3 into 1 minus turbine efficiency into 1 minus 1 upon Rp raised to gamma minus 1 upon gamma, and then we have all the brackets complete. Before that we have to subtract T1. Further, we can take T1 as common and then say Cp T1, and then say T3 by T1 as beta into 1 minus eta t into 1 minus 1 upon Rp raised to gamma minus 1 upon gamma minus 1. So this is how we can calculate Q out and Q in for a cycle which is having non-ideal compressor and non-ideal turbine. Having said this, we can move ahead and find out the formula for W net. And in case of W net, we know that W net, which is now real W net, is equal to real turbine work minus real compressor work. So we have derived just now formula for turbine work, where we have said that it is equal to Cp into T3 into eta t into 1 minus 1 upon Rp bracket raised to gamma minus 1 upon gamma minus Cp T1 upon eta c into Rp raised to gamma minus 1 upon gamma minus 1. So let us take Cp T1 upon eta c, which is this number, common from complete expression. Then we can say W net is equal to Cp T1 upon eta c into, then we have Cp which has got common, but then it becomes T3 by T1, but eta t is as it is. Since we took eta c common, we have to write out eta c into 1 minus 1 upon Rp bracket raised to gamma minus 1 upon gamma minus, in the bracket, Rp raised to gamma minus 1 upon gamma minus 1. So we can replace T3 by T1 as beta and rewrite this expression, which states that Cp T1 eta c, where we have beta eta t into eta c, 1 minus 1 upon Rp raised to gamma minus 1 upon gamma minus Rp raised to gamma minus 1 upon gamma minus 1. So here we can find out W net, which is the total work based upon the known eta t, eta c, beta and Cp T1, Rp and gamma, which are the known parameters. Here as well as what we know, we can state that eta c, eta t, beta, gamma, Cp, T1, they all are constants and then they all are fixed. So, what is unknown or what is a variable is Rp for a given gas turbine power plant. So, we can vary Rp, rest of the things are constant. So, W net is function of Rp. We can differentiate this. So, d by drp of W net, and then this we will equate to 0, and this we can rewrite as minus. So, this term would get multiplied inside, and then but this is a constant, so its differentiation is 0, and whole things will get multiplied to this 1 upon Rp raised to gamma minus 1 upon gamma, where we have Rp. So, that differentiation has non-zero value, and it is Cp T1 eta t beta into minus gamma minus 1 upon gamma into Rp raised to minus gamma minus 1 upon gamma minus 1. And similarly, whole this quantity will get multiplied to Rp raised to gamma minus 1 upon gamma, and that would get differentiated as Cpt1 divided by eta c into gamma minus 1 upon gamma into Rp bracket raised to gamma minus 1 upon gamma minus 1. But once this quantity gets multiplied by 1, it is a constant, so its differentiation is 0, so that will not come. So, rest of the things would get equated to 0. Here we can see that gamma minus 1 upon gamma will vanish, Cp T1 will vanish, so Cp T1 will also vanish, and then we can put this minus will become plus, and this will go on that side. So, we have eta t and this eta c. So, eta t into beta into Rp raised to minus twice gamma plus 1 upon gamma is equal to 1 upon eta c into Rp raised to minus 1 upon gamma. So, this leads to the fact that we have eta t, eta c, beta, and that is equal to Rp raised to minus 1 upon gamma minus we have minus twice gamma plus 1 divided by gamma, and then that we can rewrite as Rp raised to twice gamma minus 1 upon gamma. So, practically we got Rp raised to gamma minus 1 upon gamma is equal to square root of eta t, eta c into beta. So, this is how we can get an expression for the case where we had non-ideal components for the Brayton cycle, which basically includes compressor and turbine. So, this is the optimum network case. If we run the Brayton cycle with this Rp, then we can get maximum network. Here we had already derived this formula for a particular case. If we put eta t is equal to 1 and eta c is equal to 1, we see that we had derived this formula where we got Rp raised to gamma minus 1 upon gamma is equal to square root of beta, which is the condition for ideal gas turbine power plant. So this has been found out by us. Now let us find out what is the network corresponding to maximum case. So let us keep this formula intact, and in this case we will replace Rp raised to gamma minus 1 upon gamma by square root of eta t eta c beta. So we will get W net, which is now max, and then that is equal to Cpt1 upon eta c into eta t eta c beta into 1 minus 1 upon, here it was Rp raised to gamma minus 1 upon gamma, so that would get replaced to eta t eta c beta, this bracket complete, minus square root of eta t eta c beta minus 1. So we get this as the formula for W net max. We can do one thing, we can let it this quantity multiply inside, then we can write down W net max is equal to Cpt1 upon eta c. So this becomes eta t eta c beta minus square root of eta t eta c beta minus square root of eta t eta c beta minus 1. So here we can do further simplification, max as Cpt1 into eta c, here we can take square root eta t eta c beta as common, so eta t eta c beta into square root of eta t eta c beta minus 1 minus square root of eta t eta c beta minus 1. So this term can be taken common, and then we can write W net max is equal to Cpt1 into eta t eta c beta minus 1 into square root of eta t eta c beta minus 1. So we basically are having eta t eta c beta square, so it is eta t eta c beta square root minus 1 bracket square. So this is the formula for maximum network under the fact that we have optimum cooperation ratio. So having said this, now we need to find out, we need to remind this formula, since we need to find out what is the corresponding efficiency when we are operating it with the maximum compression optimum compression ratio for maximum efficiency. So we had said that W net, just now we have said that W net max is equal to Cpt1 divided by eta c into eta t eta c beta minus 1 bracket square. Now we have to find out efficiency, and efficiency is equal to W net upon Qn. Keep this point in mind, we are considering optimum Rp, so practically we are considering eta t corresponding to W net max. So that is equal to W net max divided by Qin. So further we had derived a relation for Q in, where we have said that Q in is equal to CPT1 into beta minus 1 minus 1 upon eta C into Rp raised to gamma minus 1 upon gamma minus 1. So, if we write down eta for maximum condition of network, we can write CPT1 upon eta C into square root of eta T, eta C beta minus 1 bracket square divided by CPT1 divided by beta minus 1 upon eta C into Rp raised to gamma minus 1 upon gamma minus 1. So, CPT1 gets cancelled. So, eta corresponding to maximum network condition is square root of eta T, eta C, beta bracket square divided by this eta C will come over here and it becomes beta minus 1, which is this, minus 1 upon eta C into Rp raised to gamma minus 1 upon gamma minus 1. So, this is the formula for maximum efficiency corresponding to the network which is maximum. Consider this efficiency formula and put the ideal condition, which is eta T is equal to 1 and eta C is equal to 1. We get maximum efficiency in ideal case as square root of beta minus 1 bracket square divided by beta minus 1 minus, so this Rp raised to gamma minus 1 upon gamma is practically eta T eta C beta minus 1 bracket square divided by eta C into beta minus 1 upon eta C. This is square root of eta T eta C beta minus 1. So, this formula we will consider and we will put eta T eta C beta, and where we will put eta T is equal to 1 and eta C is equal to 1. So, we have beta minus 1 minus square root of beta minus 1. So, here we practically have square root of beta minus 1 bracket square beta minus 1 minus square root of beta plus 1. So, this 1 gets cancelled and then we can take square root of beta as common. Then we have square root of beta minus 1 bracket square. We will take square root of beta common and then we have square root of beta minus 1. So, we have this as, so this leads to the maximum efficiency corresponding to maximum work, or efficiency corresponding to maximum work as square root of eta T eta C beta minus 1 square, and this 1 upon eta C will come down and we have beta minus 1 minus 1 upon eta C into bracket square root of eta T eta C beta minus 1. So, this is the formula. Further, we can multiply eta C inside and then we can get efficiency corresponding to maximum network. It is not maximum efficiency, it is efficiency corresponding to max W net, max W net as minus 1 bracket square divided by eta C into beta minus 1 minus in the bracket square root of eta t eta c beta minus 1. Now this is how we can evaluate different parameters for the case where we are having non-ideal compressors and turbines. So next things which deal with the examples of this part we will deal in the next class. Thank you.